Good morning, everybody. So it's my pleasure and great honor to introduce Felipe CUCKER today. So Felipe is a very famous mathematician who is also interested. So he started working in algebraic geometry and then moved to complexity theory, especially complexity related to numerical algorithms and working on reals. So he published several books, one which is very famous with Smale in particular as a co-author. He is the chair of the Mathematical Society for the Foundation of Computing. Foundation.
I was a chair. I'm no longer.
Okay. Let me see. So I should mention that he did his PhD in Rennes, in France. He's a scientific from the world. He was born
next to another ring.
Yes, he was born in Montevideo in South America, then studied in Barcelona, then did his PhD in Rennes, and then moved to Hong Kong, where he's a professor in the City University of Hong Kong. So today we will talk about one problem posed by Smale, the very famous field medalist, who posed 18 problems, and Felipe solved the 17th problem. So the talk today will be about these questions. So thank you for coming, and please.
Thank you very much. Does it sound okay? Yes, I see it is. Let me first say I am delighted to be here. It's, as I said, I did my PhD next to one of the other two INRIAs at the time, the one in Rennes. And just coming back to INRIA is always, for personal reasons, is always a pleasure. Let me begin. I didn't intend to do it, but Jean-Daniel told me it was a good idea to start with a web page, just a Wikipedia page, about Smale's problems. It says it's a list of 18 unsolved problems, at least 18 unsolved at that time, that were proposed by Smale in 1998. The idea was that the International Mathematical Union, probably wanting to have a list of problems that would drive mathematical research the way Hilbert's list has done in the 20th century, asked a few mathematicians to propose such lists. Of course, there were just a selected number of mathematicians, and as far as I know, the only one who ever gave such a list back was Smale. So we have this list of 18 problems, okay? And the 17 of these 18 problems, how do you, maybe like this? Good. The 17 of these 18 problems asks for solving polynomial equations in polynomial time in the average case. I put the arrow where I shouldn't, but so if you look at the right-hand side, it says that Carlos Beltrán and Luis Miguel Pardo found a uniform probabilistic algorithms, which is a Las Vegas kind algorithm for this problem. And then what really remained was, and still remains, in order to completely solve the problem, is to find a deterministic algorithm, because that is what Smale was asking for. And we did find with Peter Birgisser one deterministic algorithm, but it does not have a complexity which is polynomial on the average, but instead of polynomial, that is n to the order of 1, we found a complexity which is n to the order of log n. And actually, as I hope to be able to tell you, it is almost polynomial in the sense that for a very, very large subset of inputs, it is polynomial time. So, let me see, Alt, Cap, no, Alt-tab, yes. Good. So let me start with as I said before, the seventh problem is to find a zero of a polynomial system. More precisely, it says the following. Can a zero of n complex polynomial equations in n unknowns be found approximately on the average in polynomial time with a uniform algorithm? Okay? I will not describe at INRIA what is a uniform algorithm, and that would be silly. But I put in blue the two only things that I think need some sort of explanation. First, what does approximately mean? And second, what do we mean when we say on the average? Of course, you know what is on the average, but there must be some probability measure underlying the problem. And then is this probability measure what I want to emphasize? So let's be a little bit more precise. First, we fix a degree vector, we will call it D, D1, Dn, okay? So D1, Dn are natural numbers. And we define the space HD, this is a vector space, of all polynomials, polynomial systems, F1, Fn, where Fi is a homogeneous polynomial of degree Di in n plus 1 variables. If you look at the list of problems where Smale puts it, the first thing that Smale says is that we will go into projective space. So this is not an idea of us. Smale is saying, let's go projective. We will look for projective zeros instead of affine zeros. So what will be the input size? Okay, what's the size of an input of such a system? Okay, we will denote it by capital N, and this is simply the dimension over the complexes of this vector space. Okay, and in plain terms, this is the number of complex numbers that we need to completely specify such a system. Okay, we only need to give the coefficients of these polynomials, and this is the number of coefficients. Okay, we're going to look for 0 zeta of such a system in complex projective space. Okay, and here comes the important thing, and we consider the standard Gaussian distribution on HD. Okay, this is a multidimensional standard distribution, which has this density. Okay, now there is a trick here, and the trick is this. Okay, I am talking about the norm of a polynomial system. What will be the norm of a polynomial system? Okay, the norm square will be the sum of the norm squares of each of the polynomials. Up to here it's clear, but then for a single polynomial, what do we take as norm? The first thing you would say is, okay, you consider the squares of the, the L2 norm of the coefficients. And the answer is no, because this norm is not unitary invariant, but there is a norm which is some sort of diagonal stretching of this L2 norm that was proposed by Weil in the 1930s, that is unitarily invariant. And this is the norm that, for technical reasons, Smale proposes in his problem. Okay? So what is an approximate zero? This is a very, very beautiful notion. In general, when you're talking about approximating a zero of a polynomial, think of a polynomial in one variable, just to have a clear picture. You may talk about, well, I give you an epsilon, and I find a point such that f of x is smaller than epsilon. This is no good, because there may be no zero nearby. Then there's a second possibility. The second best is to say, okay, I give you an epsilon, and I want a point x star which is close to a real zero, a true zero x, and close in the sense of distance less than epsilon. This is no good again, because this depends on epsilon. So Smale had this good idea. For any system, and then Shub gave a projective version. For any system F, we can consider a projective Newton iteration. So I start with a point Z that I call Z0, and I consider Zk plus 1 to be the Newton map associated to F applied to Zk. Okay? And in this way I can iterate, and I go from Z0 to Z1 to Z2 to Z3 and so on. I have a sequence of points. Okay? And it turns out that if Z0 is the point I started with, is sufficiently close to a true zero, this sequence will converge immediately, quadratically fast, to a true zero of the system. Okay? So the following will happen. The distance between the ith iterate and the true zero will be bounded by a fraction of the distance between my starting point and the true zero, and this fraction is 1 divided 2 to the 2 to the I minus 1. So essentially, forget about this minus 1, 2 to the 2 to the I. So double exponential. It's converging very, very, very fast. Now, if this happens, Smale says, I call this an approximate zero. Okay? Well, here distance refers to the geodesic distance on the manifold Pn. And to simplify your life, simply think on this as the angle. Okay? A projective point is a line, and then the distance between projective point is the angle between lines. Okay? A very important remark. Systems with only multiple zeros do not have approximate zeros. This means that for a few systems, the problem is asking us something that doesn't exist. Okay? It's like if I ask you to solve a linear system of equations, and they give you a matrix which is not invertible. Okay? In numerical analysis, people say these are ill-posed data. Okay? So systems that have only multiple zeros will be ill-posed for us. So let me return to the statement of the problem. Can an approximate zero of a system in HD be computed with an algorithm that has an average running time bounded by a polynomial in N? Here, average is with respect to the standard Gaussian on the space of data, and running time is number of arithmetic operations. So this is a very precise statement of the 17th problem. Okay? Shub and Smale, they tried for many years, and they spent actually between 89 and 95 probably working on this. And eventually they published a series of 5 papers, and they laid the grounds, but they didn't really hit the nail. They didn't find the right algorithm, the final answer. Okay? Nonetheless, they propose to use homotopy methods, and this is what everybody has done since. And I will just briefly describe, because I think this is the key of my talk, to just describe homotopy methods. I will briefly describe what this is. Essentially, the idea is the following. Assume you're given to solve a problem. You don't know how to solve the problem for this data, but you do know how to solve the problem for some other data. Okay? Then the idea is I solve the problem for the data, I know how to do it, and I move very little by little from the data I know how to solve the problem to the one I don't know how to solve the problem. And eventually, just tracking down how the solution moves, I will be able to reach a solution for my original data. So consider the solution variety V, which is the set of pairs Q zeta, such that zeta is a zero of Q. Okay? I will think of an initial pair G zeta here and an input F. So you see F is the data I don't know how to solve, and G is a data that I do know how to solve, and I actually have a solution zeta. Okay? So I can consider the line segment that goes from G to F, and this consists of these systems Qt that are just convex combinations of G and F. Now, if this line does not meet the discriminant variety, for those unfamiliar with algebraic geometry, this simply means if no qt has a multiple 0, then there exists a unique lifting of this segment to a curve on V. This is my curve, gamma, okay? So I have a path going from 0, 1 to V. So it's a path in V, okay? And what I have is that is for every t, I have a pair qt zeta t, such that my initial zeta is zeta 0. Of course, and here I put this in color, since q1 is f, z1 is a 0 of f. Okay? A picture. That is more than 1,000 words. Here you have g, which is q0. Here you have f. Here I have, this is Pn. So in here, this is a part of my variety V, my solution variety V. I start with this pair, Q0, zeta 0, and what I would like to do is to move around here to reach this point, and then this projection in here will give me the 0 I am looking for. Okay? So the idea is to follow the path gamma numerically. How one can do this? Well, one can partition the interval 0, 1 into many little subintervals. Let me write to simplify qi instead of qt sub I. And doing this writing, I can successively compute approximations zi of zti by Newton's method, starting with zeta 0 equals z. So more specifically, this is important, this is what I will compute. I have an approximation for the ith system, and I will compute an approximation for the ith plus 1 system by simply applying the Newton operator corresponding to the I plus 1 system, okay, to this approximation for the ith system. Again, little picture, okay? Here is the ith system. Here is my true 0. Here is the approximation I have. And then I will consider this system here, the next one, and I will apply Newton's method for passing from here to here. Okay? What is the idea of Newton's method? Remember, the idea of Newton's method is that if I am sufficiently close to the 0, one iteration makes me much closer. Much closer, okay? Decreases the distance by a half. So if I am here quite sufficiently close, and if this distance is not too big, one iteration will bring me to be again sufficiently close, okay? But there is a point here that I didn't. There is an issue here that I didn't put in the drawing, which is the following. How much is sufficiently close? How much is sufficiently close? Well, the point is that if I am in this, if this line is gentle, if this slope, let's say, is gentle, this true 0 is very close to this one. But if the curve is going very steep up, a very tiny difference between qti and qti plus 1 will make a huge change in here. So in a way, I need to move very, very little if the curve is going up steeply. This motivates the following question. Assume that I have f of zeta equals 0. How much does zeta change when we slightly perturb the system? Okay, this is exactly our problem. How steep will be this growth of the curve? Okay, so by the implicit function theorem, we know that this projection can be locally inverted around a point around a pair if the second component is a simple zero of f bar. So the solution map G is the local inverse of this projection, and what we are interested is in the derivative of G and in its operator norm, because the operator norm will tell me how fast is going up this curve, okay? Good news, very good news, is that this condition number has an explicit form. It is the norm of f times the norm of a certain matrix. This matrix is the pseudo-inverse, the Moore-Penrose pseudo-inverse of, well, here comes a diagonal, just forget this is just a, it's really not important, this diagonal matrix. And what really matters is that is the derivative of f at zeta, and I need to invert that, okay? So I can compute this. And as it turns out, I can do better because this, you know, here I mentioned I am computing this condition number on a true zero. But if I compute the condition number close to a true zero, I can bound the error I am doing. So without giving you the details of these bounds, the truth is the following. Write D, capital D, to be the maximum of the degrees. Then this is the algorithm. This is the algorithm. And the algorithm essentially is telling me that the way I need to compute this delta t, delta tau, you see I will compute qi plus 1 such that the spherical distance between qi and qi plus 1 is delta tau. And the way I compute this delta tau is simply one constant divided another constant, the distance between f and g. Spherical distance, this will be something small. D to the 3/2, this is this d here. And then the important thing is mu norm of qi zi to the square. So this condition number here that I can compute, squared. And then I can do my follow-up, okay? And if we denote by k, you know, this k will depend on f, g, and zeta. The number, little k, of Newton continuation steps that are needed to follow the homotopy, we have the following crucial theorem that was proved by Schub in 2006. So he kept thinking on this, problems. And he proved the following. First, for all I, Zi is an approximate zero of qi. So our continuation method is very good. At any moment, I am getting approximate zeros of the true zero of the system qt or q tau. Okay? In particular, the last one, remember k is the number of continuation steps, the last one is an approximate zero of my system f, the one I am giving. Okay, so the algorithm works. This is the correctness of the algorithm. The point now is, okay, and what is the complexity of the algorithm? Well, what Schub could prove is that, actually this is not exactly Schub because he didn't give constants, but it doesn't matter. What he proved is that this number is bounded by a constant, 217, d to the 3/2, the distance between f and g, but this is bounded by pi over 2, so this is just a small constant. And here comes the crucial thing, is the integral of the condition number squared along the path. Okay, starting in 0, ending in 1 is along the path. Okay? You know, this is nice, but only God knows what is this value. It's impossible to have a real estimate on what this value may be. And this value depends on f and depends on the pair g zeta. So what can one do? Well, one idea is to randomize, okay? And then if we randomize, we can trade dependencies on condition numbers in exchange from probabilistic reliance. There are two randomizations that we can do here. First, one can, and not only one can, one should randomize the data F. This is the average analysis that was requested by Ismail. And we know that we should randomize because, as we said at the very, very beginning, there are ill-posed systems, and if a system is ill-posed, the complexity will be infinite. I mean, my algorithm will run forever, okay? Second, we can randomize, and that's interesting, on the initial pair. That would give a randomized algorithm, and that was the idea of Beltrán and Pardo. There is a moral difference, but, well, here I am talking stripes to the tiger. The probability distribution for the initial pair is completely irrelevant as long as we can efficiently sample pairs from it. Okay? Because it's something I choose to do in that way. The distribution for F is supposed to model the elusive notion of frequency in practice. So some people will complain against this, okay? But we are using the one that Smail proposed, so that's fine from a theoretical point of view. Okay, what we did was, actually with Peter, we were worried about this, and what we did is to work on the solution that people in general try to do to avoid this problem of average analysis, and is to do the smooth analysis as proposed by Spielmann and Teng. But I won't talk, in this talk I will not mention this, okay? So I will not go through this. So let me go to the randomization of the second, randomization of the pair. We don't know how to construct a good initial pair. That's, believe it or not, today, 2014, is an open problem. Nobody knows how to construct a good initial pair, okay? Hence, we choose it at random, and this is fantastic, because we don't know how to construct initial pairs deterministically, but at random, you choose one at random and it will be good. Now, the problem is, how do you do that? Well, the measure would be the following. Let me first describe the measure. We choose G from the standard Gaussian. Good. Then as it happens, the number of, with probability 1, the number of zeros of G is this capital D, which is the product of the degrees, and it's called the Bézout number. Okay? So with probability 1, I have Bézout number different zeros of my system. So part 2, I choose one of the D zeros of G from the uniform distribution. Now, here we are in a big problem because you say, okay.
Find the zero of F, find the zero of G.
Yes, I mean, finding a zero was a problem we wanted to start with. So there is something fishy here, okay? And here is a breakthrough. And then this is, in my opinion, the most important things that Beltrán and Pardo did. And it's really a breakthrough. They massaged this distribution to represent it in a different way, okay? They managed to look at it in a different way and to come with an algorithm that can sample from this distribution. I will not give you the technical details, but just to give you an idea of what could that be. Suppose you are giving a polynomial in one variable in degree 5, and you want to sample a polynomial with a 0. Then one thing you could do is the following. You sample you sample A and B, you consider AX minus B, you know that AX minus B has a 0, which is minus B divided by A, and then you sample a polynomial of degree 4 at random, and then you multiply your polynomial of degree 4 by this one of degree 1, and you obtain a polynomial which is random, of course, because A and B were random, and the degree 4 is random. It has degree 5, and you know a 0, namely minus B divided by A. Their idea has this flavor, okay? And it works. So here is the Las Vegas algorithm. I am given an input F. I draw a pair G zeta at random from this solution variety. And then I run, I run the adaptive linear homotopy that I just described on my input triple F G zeta, okay? Of course, this is a randomized algorithm, and then I should consider expected running time, randomized running time. And this is, for my input F, for my data F, is simply taking the expectation over all pairs G zeta of this number of steps. This is not exactly the running time. You need to multiply by the cost of each iteration, but the cost of each iteration is a factor capital N. So, okay, no problem with that, okay? So this is what really matters. This expectation can be put as the expectation of first expectation over drawing the G, it comes from here, and then a discrete expectation. Okay? So, what are the possible frameworks we have? My pair, G zeta, my initial pair, can be deterministic or random. And my initial data, I can consider deterministic or random as well. What Smale asked in his 17th problem is that, say, consider F random, because you're going to consider average case complexity, but your algorithm should be deterministic, so you cannot randomize your initial pair. Okay? So in this box, we have Smale's 17 problem. When you have an F and a G, Bezout 6, I think, is the best you can do. Okay, this complexity bound in terms of an integral. So let's put it there. But then we have here two boxes. Okay, two other boxes. The first one was is just the result of Beltran and Pardo. They show that this expected running time, this randomized running time, if you now take the average over your data, which is what Smale was asking for, the whole thing, so you see here you have eliminated all dependencies on F, G, and zeta simply by randomizing. Everything disappears. And what it results is order of d to the 3/2, capital N, little n. Okay? So it is a little bit above linear for the number of iterations, and then a little bit above quadratic for the total cost in arithmetic operations. Okay? So this is a probabilistic solution of Smale's 17 problem, and it fits here because both F and the pair G zeta are random. Now, in a way, this box here would be to consider F deterministic, but to still allow randomization. In a way, it's saying, well, okay, what can I say if I am given an input? I don't want to randomize. I have an input, F, which is given to me, and I want to know how difficult it is to solve this F. Okay? Then I can randomize my initial pair. The idea is then the following. Your running time will have to depend on how well conditioned is F. For instance, if F has only multiple zeros, your time will be infinite. So how can what can I say? Well, I consider this condition number for F, which is the maximum over all zeros of the system F of the condition number of that particular zero. Okay? And then what we found is that the condition number, the number of Newton steps for F on the average for your initial pair is d cubed, a little bit bigger than the d to the 3/2, capital N, little n, that's exactly what we had before, and here we have the square of the condition number of f. Okay? So this is, allows us to fill this box here. And finally, probably this is the really most interesting result. We could eliminate randomization at all. And what we prove is the following. There is a deterministic algorithm for Smale 17's problem that takes on standard Gaussian input f an expected number of arithmetic operations tf, which is bounded, as the Wikipedia page says, by n to the order of log n. Furthermore, you give me any epsilon greater than 0, and then this algorithm is polynomial time on the average when restricted to systems such that the degree d does not belong to the interval n1 minus epsilon, comma, n1 plus epsilon. So essentially what's going on is that my algorithm has this upper bound, just this complexity upper bound, just when the degree d, the maximum degree d, is very close to the number of variables. The moment it's a little bit far away from the number of variables, it behaves very, very well. And the idea is very simple, and we were a little bit surprised when we worked it out, because we realized something very, very silly. I don't know how many of you have been working in computer algebra or, solving polynomial systems. Absolutely all algorithms for solving polynomial systems are unfortunately exponential time, but their exponential dependence is always on the number of variables. That's what people call the curse of dimensionality, okay? The dependence on the degree is always mild, okay? So in general, the dependence on the degree is, the complexity is of the form d to the n. Actually, kd, k is then, yeah, forget, d to the n, okay? And what we realized is that we could take one system, fixed, which is this system, that has the following property. The mu max is of the order of n to the d. So using something similar to the previous result, fixing this initial system with any of the zeros, we had an algorithm that would take time n to the d. So it was exponential time, but on the other way around. No curse of dimensionality. It's polynomial in n and exponential in the degree. And then the idea was clear. Okay, if the degree is smaller than n, we ran our homotopy algorithm with this initial system and the 0, 1, 0, 0, 0, 0. For d greater than n, we use symbolic methods. Symbolic methods are exactly the opposite, d to the n. And where do we have problem? Where? When n is close to d. Okay? So we could somehow put our theorem 2 in here. It doesn't finish, it doesn't completely solve Smale 17 problem. So if you're interested, it's still open. So we did it out of generosity with the future generations, and not because of incapacity, of course. And this is a more or less old paper, okay? It was published in November 2011. Okay? So let me mention a few things newer. First, I don't know whether it's worth to enter into the details of this, but just to... So in all the work that had been done in... Let me explain without going to the technicisms. Okay, I think it's better. In all the ways, all the work that had been done for SMAIL 17, all papers assume infinite precision. That is, all papers assume that you can have real numbers and you can operate these real numbers with infinite precision. Most analysis of algorithms in numerical analysis are in general done that way, but then also in general, traditionally, at least for numerical linear algebra, there is a very strong tradition of doing finite precision analysis and trying to understand, can I really do this without any big trouble? And in a way, I had the idea that this had to be true here, because look what we are doing. We never are computing anything really exactly. We are always computing, we are following a path. We are never exactly on this path. And the only thing we are doing is computing points z, which are approximations to the true zeros zeta. If I do a little mistake in my approximation, I will still be having an approximation. And I can modify, I can tweak my algorithm to ask it to be a little bit more, let's say, rigid, and that will take me, let's say, twice the number of steps. But then I will be sure that the mistakes, the rounding off mistakes, will not damage my solution. Okay? And together with Irénée Briquel, oh, yeah, this is a PhD student of mine from France. Okay, it's a PhD thesis done in joint supervision between École Normale, Lyon, and Hong Kong. Supervisor in Lyon was Pascal Coiran, who also spoke in this colloquium long ago, but not so long ago. And Javier Peña and Vera Roshina. And we proved theorems showing that things go well, both for fixed precision and the most interesting result for variable precision. But just explaining what is fixed precision and variable precision is more technical than really interesting. Okay, actually it can be boring. So let me skip and just keep the idea that, yes, if you have finite precision, your algorithm will work very well as well. So let me give you a last result. And this is hot from the oven, it's still not published. Okay? The previous paper was published, I think, maybe a few months ago. This is still unpublished. When you look at one of the, consider the eigenvalue problem. This is quite amazing. I mean, I talk with people and everybody says, oh, the eigenvalue problem is solved. I mean, it's easy. I mean, you go and you use MATLAB or any, and they have algorithms that compute eigenvalues and they are very good. And the truth is, yes, they are very good. But theoretically, it's an unsolved problem. What is the situation with the eigenvalue problem? We came up with algorithms, several, for which either the complexity is well understood, but they are numerically unstable in practice, or, and these will be other algorithms, they exhibit a very stable behavior numerically, but they defy a complexity analysis. Let me give you examples of the two cases. The first case, okay, I'm giving a matrix, A times A square, n times n square, okay? A. I compute the characteristic polynomial, chi A. And once I have the characteristic polynomial, which is a polynomial in one variable, complex coefficients, I computed zeros. And there I got the eigenvalues, okay? Good. As it happens, practitioners never use this. Never. Why? Because they complain that systematically they start with matrices which are well conditioned with respect to eigenvalue problem, that is, small perturbations in the matrix will cause small perturbations in the eigenvalues. And when they compute the characteristic polynomials, they found polynomials which are poorly conditioned. That is, small perturbations in the coefficients of the polynomial may cause huge perturbations of the eigenvalues, of its zeros. So, no good approach. So what is the good approach? Well, another one, which is today's algorithms of choice, is the QR iteration with implicit shifts. Now, looking at this book by Jim Demel, who is probably one of the big names in numerical linear algebra, he writes, it is interesting that after more than 30 years of dependable service, convergence failures of this algorithm have quite recently been observed, analyzed, and patched. But there is still no global convergence proof. So people are using an algorithm for which there is no proof of convergence, even though the current algorithm is considered quite reliable. So it works in practice, but in theory, nobody knows why. And he finishes, so the problem of devising an algorithm that is numerically stable and globally, and he even adds, and quickly, because globally convergent will only show that the algorithm is correct, will only show correctness, but will not show nice complexity. And so he adds, and quickly, convergent remains open, okay? Well, if we go to, we can try to start, so our idea was, oh, maybe one can do something with homotopy methods for the eigenvalue problem and try to find one algorithm that is stable. We know homotopy is stable, homotopy method. It's just a, you know, I have just shown some theorems saying that it's numerically stable. But in addition, we will be able to prove some sort of polynomial time convergence, you know, expected time, let's say. But let's start by a simpler one. And simpler would be symmetric, or in the case of complex matrices, Hermitian. In a way, one could think that so there are still open questions with regard to the QR. We still don't know how fast the QR algorithm with shifts works, even for Hermitian matrices. And then Percy Deift was putting very recently this as an open question in matrix theory. Random matrices. So how fast does the QR converge in this for Hermitian matrices? If we actually, he talks about symmetric, that is real matrices, and then he takes the Gaussian orthogonal ensemble as the underlying probability distribution for these random matrices. And just to, this is very, very simply, what is a GOE matrix H? A GOE matrix H is simply 1/2 of, you take a random Gaussian matrix, an arbitrary Gaussian matrix, you consider the transpose, you do the addition, this will be symmetric, and you divide by 2. So it's very, very close to Gaussianity, but you enforce symmetry. Now, what we did with Diego is to use homotopy methods. We worked only on the complex case, so instead of Gaussian orthogonal ensemble, you need to consider what is called Gaussian unitary ensemble. And then your matrix, your random matrices H will be 1/2 of G plus G adjoint, okay? Consider the conjugate transpose instead of simply transposed. And this is the theorem we proved with Diego, we describe a randomized algorithm which, given an n times n Hermitian matrix A, returns an approximate eigenpair lambda v of A. In addition, this is nice. What we give is not an eigenvalue. We return the eigenpair. This is very, very important because even if you have an eigenvalue, your eigenvalue will never be exact, right? Because of Galois. Galois tells us we cannot compute zeros of polynomials in an exact manner. So we will always have an approximation of the eigenvalue. But if the eigenvector is poorly conditioned with respect to the eigenvalue, what we will compute has nothing to do with the true eigenvector. Instead, working with eigenvalues and eigenvectors together, and actually we follow the path in the space of triples, A lambda V, we compute an eigenpair lambda V of the matrix A. And this approximates in the sense of Smale. You do a couple of iterations with Newton and you get a very, very close approximation. The average cost of this algorithm over the random choices made by the algorithm, and assuming A drawn from a G distribution, is bounded by order of n6. Two things. First, this is not meant to be a practical algorithm, okay? There are practical algorithms that work much better than ours, okay? So this will not be used in LAPACK tomorrow, nor the day after, nor in 5 years' time, okay? Because there are algorithms that work much better. But it's an interesting theoretical result because it shows that this can be done in polynomial time. So the algorithms that are used in practice are have a complexity order of n cubed. So our algorithms is a disaster, is slow as it can be compared with algorithms that are used in practice. Second, this is fantastic. There is a caution here that I put out of honesty. It says, this theorem relies on an assumption on the cost of certain random number generators. So the point is that we need to generate random initial pairs, and for this, essentially what we need to do is we need to we need to generate at random the eigenvalues lambda 1, lambda n of a G matrix. And we gave an algorithm for this, but this algorithm somehow relied on some assumptions that we couldn't really verify or check or even attempt to show because they have to do with random number generators, and this is definitely not my field or even Diego's. Okay? So in the paper, it is written this assumption that we rely on, and on the talk, of course, I wanted to be honest and put it here. But before yesterday, I was talking with Laurent Mertz, who works at the Université de Nice, and Laurent was aware of our paper, and he showed me a couple of very, very, very recent papers, published in 2013, one of them, and one of them published in 2013, and the other two unpublished as of today. They have been put in archive in 2013, but unpublished, who deal with exactly that. And actually, they show essentially what we needed. So you can remove this caution. Okay, I didn't bring my LaTeX file, so I couldn't remove it yesterday. I just brought my PDF, but the caution, you may remove it. It's no longer necessary. I mean, what we were assuming has been shown very recently. And that's the end of my talk.
In the randomized algorithm that you describe, do you have estimates for the variance?
The answer is no and yes. The answer is no, I don't have them, but the answer is yes. Schub and Carlos Beltrán wrote a paper about the variance. it's not the variance of the running time, but it's almost in a way, because what they did was, so all these complexity bounds for a number of steps depend on finding appropriate bounds for the expectation of the condition number of a random pair. Okay, if you sample from this distribution on V, on the solution variety, you will get a pair, and what is mu norm of this random pair. And then there are bounds for the expectation that they are used and again for getting complexity bounds. But Beltrán and Schub, they have shown also bounds for the variance. As far as I know, nobody has used these bounds for the variance to derive bounds for the variance of the running time of let's say, the algorithm. But, but that probably could be done.
So in the analysis, you consider a down system, a homogeneous system over Pn, but in some problems, you have also a structure, maybe you have a fixed support, or you have some multi-homogeneous structure, and so on. So does the analysis extend to this case?
I would love to. I would love to. Look at the following. Yeah, I have thought about it, and the number of results or the number of clever ideas that I have gathered is zero, nil. But I would love to. Why? Because if you look at the transparency on the deterministic algorithm, I don't know what, maybe going back. We look at that system. This system has only 2 coefficients, okay? Only 2. So it cannot be more sparse in the sense you are mentioning. So one thing I thought is, okay, what happens if I have some sort of sparse system? Then I can start the homotopy with this one, and essentially I will have whatever is the support, as you, in your words, the support of my data, plus at most 2 more coefficients, which are the coefficients here. So essentially, I will have a very, very small support all along the homotopy, but because convex combinations of 2 polynomials do not introduce anything new in the support. And I was dreaming that something could be proven, but now I am more realistic and I understand that not by me. I would love to, but...
In your solving system, you use only the first derivative of the system to get approximate 0. Why don't you use the second order derivative, which may allows you to increase the steps, the size of the steps between the continuation method using Kantorovic's theorem, for example?
It's a good question. So I never really seriously considered of doing that, but my impression is that using a higher derivative will probably not increase that much the time. It will increase. It will decrease the time. That's for sure. The number of iterations. Let me put it that way. It will decrease the number of iterations. But my gut feeling is that this decrease will be compensated by the cost of each of the iterations, because you will have to compute Hessians and this. So it will be, in a way, it will be bigger. So my gut feeling is that it may not help. And then here comes the problem. When you have the gut feeling that it may not help, just consider it. It's a huge amount of work, doing the work for something that at the end will not yield any fruit. That's why I never did it. But yeah, it's an idea.
You can imagine, for example, the system of quadratic equations.
Mhm.
Relation is constant, so no cost.
Yeah.
And with big increase, it's time step.
That's an idea, yeah. That's an idea. And in addition, the system of quadratic equations is precisely the one that we deal with it best. Because for this you see, the mu max is n to the square. So it's the one in which we're working with I mentioned before, we don't know how to get, how to deterministically construct a nice initial system. Now I try to retract a little bit myself. We do know if the degree is small. We do not know in general, but if the degree is small, we do know. And degree 2 is the case in which we definitely know. I mean, the mu max is n squared. So yes, for this one, if there is any way of just further decreasing the complexity, that would be nice. No, and it hadn't occurred to me. Yeah.
Wait a minute.
Now you are just considering algebraic equation, and what about non-algebraic equations?
Yeah, I really don't, yeah, no idea. No idea. Maybe part of it could be done, but some other parts may be more difficult. Let me just give you just one, because of course I didn't give you all the technical details, but let me just describe a few technical details, okay? One of the very, very beautiful theorems that Smale proved at the very beginning is when he was developing this theory about approximate zeros, is the following. Assume you have a zero of a function, okay? Not a system, a function, okay? From Rn to Rn, from Cn to Cn. You have this zero, zeta. Assume it's a simple zero, okay? So it has approximate zeros. Can I give a bound on a radius r such that all points in the ball of center zeta and radius r will be approximate zeros? And the answer is yes, we can give a bound. The bound was given in the terms of invariant of the function f and your zero zeta, which Smale called gamma of f zeta, okay? Until here, and we use it, that's crucial. We use it to prove that when we are following the path, we are always in the union of these balls, okay? So essentially what you have is you have the path, and you have something that goes like this around your path, okay? Sometimes it's wider, sometimes it's thinner, depending on the gamma. Crucial to work these things is that in the case of polynomial equations, the gamma is defined in terms of all the derivatives of your function. And in the case of polynomial equations, you can show that this bound gamma reduces to a bound on only your first derivative. And here is where the d to the 3/2 comes from, by the way. There is a d to the 3/2 coming into, but that's it. You know, d to the 3/2 is no big deal. So essentially, you can reduce this gamma estimate to something that only depends on the first derivative. The moment you replace polynomial system by something which is non-algebraic, the gamma, what is called the higher derivative estimate for the gamma, will no longer apply. And then, unless you come with a great idea, the whole thing will collapse. It's not the method. Maybe the method will work, but proving that the method works will collapse.
So I have a question about how far are you from say, practical implementations, and that may be as efficient as
Okay, let me first say that...
And is it a question of research, or is it or algorithms, or questions of implementation?
Oh, okay, let me first start with, what we did with Peter was, in a way, absolutely theoretical, and what we wanted, like anybody else, is simply to write a paper. And we somehow were lucky, and we came up with a paper that was much better than we originally expected. In all honesty, it was like that. I mean, little by little, we started proving things, and we realized that you could go further and further, and almost solving the problem, okay? Once said that, from a practical viewpoint, a randomized algorithm is as good as any other. I don't have anything against randomization, you see? It's just that Smale didn't put it in his 17th problem, but from a practical viewpoint, a randomized algorithm is fantastic. So I don't think that what we are doing is, you know, now, Carlos Beltran, together with somebody called Anton Laking, they did implement the randomized algorithm. And Carlos is very clever, but I don't know whether he's that good implementing things, but Anton is fantastic implementing things. I mean, that's in this sense, that was a very, very good mix. And they have a couple of papers where they describe details of the implementation and the numerical runs and things like that, things they obtain. Yes, it's practical and it works. And the fact that it's guaranteed, it means that when it finishes, you do know that you have an approximate zero. You have it. You can check it if you want, because there is a test for that, but you have it. And then you can apply Newton method, let's say, 10 more times, and you get 2 to the 10, you know. You get an approximation which is very much beyond the computer accuracy. But there is another thing that one should add here. There is a group of people that work in homotopy methods after a very long time, and they are practitioners. And the implementations they did are way, way faster than anything that Carlos or Peter or myself could do. Because what they do is, when they notice that they can gain a factor of 2 by tweaking something, they do this tweak. And so the algorithms go very, very fast. But of course, it's impossible to prove anything, because they made so many tweaks that the theoretical side is a nightmare. Okay? So, to be very honest, from a practical viewpoint, best algorithms with homotopy are done by people like T.Y. Lee, who is in Michigan, or Jonathan Hauenstein, who is in Texas. I mean, there are a number of people who have done, you know, practical implementations, and they are very good.